Hi everybody, welcome back. We are ready for graphing trigonometric functions. Today we're going to focus on tangents and reciprocals. This is going to go along with lessons 4.5 and 4.6, I think mostly 4.6 in your textbook. And a little warm-up for you, so go ahead and pause your video. This is review from first semester. You should be able to do this on your own. Alright, so what you should have found is that you had an amplitude of 2. You had a period of 8 pi, so your first mark in your graph here is going to come all the way over to 8 pi. That means it takes 8 pi units to complete one cycle. And then you're going to go ahead and graph those two things with a sine curve starting at the origin. Your 5 key points need to be there. And then, of course, all you need to do is take care of your phase shift and your vertical shift. Remember, the phase shift is inside the parentheses. It's going to go backwards of what you think it's going to do. And they were nice enough on this problem to go ahead and factor the phase shift away from the B value, which gets you your period. So once again, that should just be a warm-up for you, a little review. We're going to need that skill here in just a minute. All right, fast forward, let's get into some tangent. So tangent, we figured out from the first half of this chapter, is really just the sine curve divided by the cosine, okay? Or the sine value, rather, divided by the cosine value. So keep in mind, anywhere cosine is 0 is going to create an undefined answer for tangent. And anywhere that the sine curve is 0 is going to create a 0 value for tangent. So it should be no surprise that not only does the sine have an x-intercept of 0, the tangent also has an x-intercept of 0, and the tangent has an x-intercept at pi. So this is pi. So if it takes me pi units to complete and get back to another x-intercept, my period for a parent tangent is going to be pi instead of 2 pi. Keep in mind we're still going to be dividing by that b value, which would go, oops, not right there. The b value is going to go interior by the x and take care of a horizontal stretch or shrink force. We'll do those in just a minute. Now, interestingly, amplitude would normally come from a vertical stretch value in front of the tangent, but amplitude was also defined as half the maximum minus the minimum, and the tangent curve actually goes up and down forever, so there is no amplitude. Never ever say that there's an amplitude on tangent. Now, does that mean we can't reflect it? Does that mean we can't do a vertical stretch? Of course we can. We can still do a flip. We can still do a vertical stretch. So watch out for those two things. They're still going to come from this a value, just like they did in a sine and a cosine. Okay, so back to the vertical asymptotes concept. Cosine of x is 0 when the cosine curve is at pi over 2. So on our tangent curve, we should always be drawing vertical asymptotes at pi over 2 and negative pi over 2. Another way to remember that, well wait, let's write that down first. So it's a vertical line, it's going to be x equals. It's actually going to be only the odd multiples of pi over 2. Because if k was even, if k was 2, 2 pi over 2 is just pi, and we've already decided that that was an x-intercept, so that doesn't work. So we're going to say that the vertical asymptotes are x equals k times pi over 2, where k is going to equal the odd integers. Now, I have a lot of students who go, do we have to write that? You have to be able to identify vertical asymptotes for a specific tangent curve. If the specific tangent curve happens to be the parent function tangent, then yes, you have to somehow tell me that it's only the odd multiples. If you prefer to list a few vertical asymptotes, etc., that would be fine too. Now, another thing that's going to help you with drawing tangent is that these vertical asymptotes will always be or occur at half the period. Okay, so if my period changes, my vertical asymptotes also change. It's just a horizontal stretch. Okay, now we do have a few key points. We mentioned a second ago we would be able to sometimes vertically stretch tangent. So the key points that we're going to want to remember is that if we take, let's see, this was negative pi over 2, and this was negative pi. So we've got our period, we've got half of our period. And if I take and come in here and I take half of those marks, chop those all in half, in this case that would be at pi over 4 and at negative pi over 4, or again, half of wherever the asymptotes are, and I go up 1 unit. Let's see, pi over 4, that's 45 degrees. What's the tangent of 45? 1. Are y'all saying it? I don't have Mr. Lecky here to tell me. It's 1. Okay, so wherever you have your 1 mark, and your negative 1 mark, negative pi over 4, remember that's just an angle. If we start here, we go down instead, and we're going to have negative 1 be our tangent value. So this mess that I've made now, our tangent curve goes through some key points. It goes through 0, 0, okay, the parent function does. It goes through pi over 4, comma 1, and it goes through negative pi over 4, comma negative 1. And those are going to be our 3 key points, along with at least 2 vertical asymptotes, and that gets us our 5 key features for the tangent curve. All right, we should be ready to give it a try now. Okay, next problem. So we've got y equals 1/2 tangent x over 4 minus 5. So let's identify some things we know. We know that the amplitude is, no, not 1/2. There ain't some. There is no amplitude. However, there is a vertical stretch, now in this case a compression I suppose, vertical squish if you prefer, okay, vertical compress of, or by a factor of 1/2. It got squished. Okay, period. So the period is normally pi, and we're going to divide it by the v value. The v value in this case is 1/4. So when I take a pi and I divide it by 1/4, I actually stretch to a 4 pi. Okay, so we're going to come over onto our graph. I know your graph doesn't have a grid on it, but your homework will because you're going to use graph paper, so it'll be okay. All right, so we're going to come over here and we're going to go to 4 pi because that was our period. We're going to chop it in half. Boy, this sounds kind of familiar. Now this time, instead of chopping it in half again, I'm going to wait a second, and I'm going to reflect it. So I'm going to reflect it over here to a negative 2 pi and a negative 4 pi, sorry. Reflect that scale. Okay, so remember, if I complete one cycle, I'm going to have an intercept, and I'm going to have an intercept, and I'm going to have an intercept. Okay, so if I go all the way to the end of my period, I'm going to be at an intercept. If I chop it in half, I'm going to be at an asymptote, you guessed it. So here I have a vertical asymptote, and at negative 2 pi I have a vertical asymptote. Now I'm ready to chop it in half one more time, cut the distance in half from this intercept at 0 to that asymptote, and I have a 1 pi. Okay, negative 1 pi. Now when you chop it in half again, please use that scale all the way through the entire picture that you've drawn. Don't cut it in half here, but not there. Okay, that's bad math. It's a PA, poor algebra. Okay, so now what we know is we've taken care of our period, we've got our scale all set up, and we are ready to draw our tangent curve with an amplitude of 1/2 instead of 1. So remember those key features when we talked about our pi over 4 being 1 box up? Well, now I know that my pi over 4 is 1 box over, in this case it's pi, and I'm going to go not 1 box up, but I'm going to go half a box up and half a box down. Okay, so this is now my modified parent tangent curve. Why did I draw it dashed? You guessed it, I didn't deal with the negative 5 yet. So there is no phase shift here. Phase shift is none, but there is a vertical shift. So all I need to do is take all my dots and move them down. Now if it's a vertical asymptote, which goes up and down forever, and you move it down 5, it's still in the same place. It's only if you move it left and right that you have to deal with the vertical asymptotes moving, okay? So all I have to do is take these 3 dots, move them down 5 units, 2, 3, 4, 5 units. Now I'm at negative 4.5, and I'm at negative 5.5, and there's my negative 6 mark apparently. Alrighty, now I can draw my tangent. Now you spend all this time finding these beautiful asymptotes. Please make sure that you draw your graph towards those beautiful asymptotes. And again, label your beautiful asymptotes. This one is at x equals 2 pi, and this one is at x equals negative 2 pi. You could also write off to the side VA and clarify what those are. Alrighty, there's our first tangent graph. Again, I recommend you pause the video and go ahead and give the next one a try. Okay, so this is what I would classify as more of a hard question, because I don't know if you noticed, but that 3 is not where it belongs. It needs to be factored out. So let's go ahead and change this. We're going to have negative 2 tangent of 3 times x minus, I need to multiply 3 by something, but end up with pi over 2 at the end. Well, how about if I do a pi over 6? Because 3 times a pi over 6 would make a pi over 2. Okay, we are ready for amplitude. There isn't any amplitude. No amplitude. But there is a vertical stretch of 2. And this time we're going to flip it over the x-axis. Okay, period. Period is normally pi. We start with the pi, but we're going to divide it by the b. The b was a 3, and so our period is pi over 3. So let's get our scale set up over here. We're going to come out 4 boxes, or an even number of boxes. We're going to go pi over 3. We're going to chop that in half and go pi over 6. I'm going to flip it onto the other side and go negative pi over 6 and negative pi over 3. So far, what I know is that the end of my period right here is an intercept. The 0 is an intercept. The negative pi over 3 is an intercept. I'm actually graphing 2 periods here. And the pi over 6 is my asymptote. And the negative pi over 6 is my asymptote. Nice symmetry here. Okay, now I need to chop those in half again to be able to do my phase shift. Okay? Because I need the original points. Okay, so I need those key points which are halfway from the 0 origin to the asymptote. Okay, so half of a 6th is a 12th, and this will be 1 pi over 12. 2 pi over 12 would be my asymptote. 3 pi over 12, you can mark it as 3 pi over 12, but in case you're curious, that's the same as pi over 4. Okay, and over here we're going to have negative pi over 12 and negative pi over 4. Okay, so now we are ready to do a little shifting. Actually, let's wait a second here. Let's get our key features, key dots on here, okay? So we're still working with a vertical stretch of 2 and a flip over the x-axis. In this case, since it's negative, we're actually going to go down 2 boxes. Parent, tangent. This is the tricky part, and this is the part where if you don't want to draw that parent tangent, I'll let you, because it gets very, very messy on your graph, okay? Our phase shift. Whenever you have a phase shift with tangent, everything is going to move to the left and the right. In this case, it is a positive pi over 6, which means this little asymptote at negative pi over 6 is going to move to the right pi over 6 and be this asymptote. Okay? And it gets awfully messy trying to graph it. So it's up to you if you want to graph the parent function off to the side, the modified parent function off to the side, and then create a new graph with the same scale, maybe right below it, and you could see the shift. Totally up to you, okay? The next thing I come to is this dot, and I need to move it left pi over 6, which is 2 boxes. It will be right there. The next thing I come to is the dot, the origin. I'm going to go, not left, I said left, right, pi over 6. The next dot I come to is at pi over 12, negative 2. I'm going to move it to the right 2 boxes, or pi over 6. And the last thing is this green asymptote right here is going to get moved to the right 2 boxes, and it will be this new red asymptote right there. So now our curve is just doing that. Again, it's only one curve of tangent function, but it is one whole cycle because it went from an asymptote to an asymptote. Okay? Alrighty, I think that's enough graphing of tangents. Now let's get into the reciprocals, the rest of the 6 functions that we have. Okay? So the first one we're going to deal with is cosecant. Start off knowing that cosecant is simply the reciprocal of the sine curve. So notice we've drawn a sine curve for you. Okay? All right, so how do we make the reciprocal functions? Well, back to that idea that tangent was undefined when the cosine was undefined. If cosecant is the reciprocal of sine, then it's undefined wherever sine is 0, because that makes you divide by 0. Okay? It's undefined wherever I go 1 over 0, which means wherever I go 1 over sine of x, question, when does the sine of x equal 0? Well, the sine of x equals 0 here, and here, and here, and there, and there. So negative 2 pi, negative pi, 0 pi, and 2 pi. And that means that every one of those blue dots, if you will, for cosecant will be a vertical asymptote, because you can't divide by 0. Okay? So now, your paper has a few more questions on it that talks about where does the sine curve 0. Again, you could look at the sine curve, you could look at the unit circle. The sine curve is 0 on the unit circle. The sine value on the unit circle is 0 whenever we're along the x-axis, which gives us angles of 0 and pi and 2 pi. Okay? Same thing. That's the cool part about this trig stuff, is it all works together and you can think about it in more than one way. So, notice that when I draw my asymptotes, I'm not just stopping. They go up and down forever. Okay? But do keep in mind that the vertical asymptotes happen wherever the sine curve equals 0. Okay, that's going to be important in a minute when we try the other reciprocals. All right, so we need some more dots than just some asymptotes, okay? So let's try to find some other values. If you're following on your notes, we're on this question. What angles make a sine equal to a cosecant? In other words, what number is equal to its reciprocal? Well, the only two I can think of are 1 and -1. So, whenever the sine curve is 1, the cosecant is also 1. And whenever the sine curve is -1, the cosecant is also -1. So the blue dots appear on both the red graph and the cosecant graph, which is the one that we're creating. Okay, so now we've got some dots, we've got some asymptotes. What's going on from here to here? That's my next question. What's going on between one asymptote and that maximum on the sine curve? Okay, so let's pick a value. Remember that the sine of pi over 6 is 1/2. You should know that. That's a special right triangle, or it's in your chart. Okay, so if the sine is 1/2, what's the cosecant? Well, isn't it 2? Isn't it? It's reciprocal. Okay, so where is the sine curve? Pi over 6. And that's where we get a sine value of 1/2. So the cosecant at that same x value is going to be way up here at 2. In fact, wherever the sine curve, every multiple of pi over 6, 5 pi over 6, 7 pi over 6, okay, all those, well, not 7 because that's negative, but all those values where the sine curve is 1/2, the cosecant curve is going to be 2. So if I ignore these little dots because they're actually, that's not the color I meant. If I ignore these dots right here because those are actually on the sine curve, there we go, let's erase them. And I just look at the blue dots, what's happening? The closer and closer the sine curve gets to 0, the bigger and bigger the reciprocal gets to infinity. So it's going to approach my asymptote. The same thing will happen on the negative side. The closer and closer the sine curve gets to 0 from the negative, what's the reciprocal of a negative number? It's still negative. So the cosecant curve is going to get closer and closer to a negative infinity. And what we end up with are these little flipped over pieces of sine curve because it's a reciprocal. Only the flipped over pieces go up and down forever. The blue graph only, including the blue vertical asymptotes, is our cosecant. So we should hopefully see the pattern that between the asymptotes, the cosecant goes shooting to infinity or to negative infinity. All right, so what about the other two? That was a long explanation, but basically you need to remember just a few things, okay? Wherever the curve is at an x-intercept, its reciprocal is at a vertical asymptote. So let's take a look at secant. Secant is the reciprocal of cosine, correct? These two things are equivalent. So wherever cosine is 0, aka right there, right there, right there. So this means we're going to have to be able to graph a sine curve and a cosine curve first. Remember our warm-up? We might have to be able to graph a new fancy sine curve or cosine curve. But then after we do that, then all we have to do to get to the secant, in this case, is find our asymptotes, which will be at the intercepts. Okay? And remember that wherever cosine is 1, the cosecant is 1. The maximum of the cosine is the minimum of its reciprocal. That makes sense. You're flipping fractions over. The minimum of the cosine is the maximum of the cosecant. And frequently, sometimes you'll see these pictures drawn, and it looks a little confusing at first because they'll go through and they'll draw it like that, and you're like, where's the other half? Does that mean I'm supposed to stop? They just happen to graph it on whatever domain they happen to graph it on. You have to have at least one period, which means you have to start to repeat your cycle at least one time. Okay, so there's our secant, works with our cosecant. Okay, cotangent is a little bit trickier. We have our cotangent drawn here. Let me get our asymptotes in. Well, actually, I'm not going to draw the asymptotes. The asymptotes would be here and here, correct? Pi over 2 and negative pi over 2. We found that out a couple of slides ago. Okay, we'll come back to that concept. I don't want my picture to get too messy here. So again, cotangent is the reciprocal of tangent. So 1 over tangent of x. Oops, that's an x. Okay. Wherever tangent is 0, cotangent is going to be, again, undefined. So that works for all three reciprocals. The intercept of the original is an asymptote for its reciprocal. Okay, that makes it pretty easy to graph. Now, what about the asymptotes of tangent? The asymptotes of tangent came from dividing by 0, and if I take number divided by 0 and I reciprocate it, don't I have 0 divided by a number? Huh, that's an x-intercept. So the intercepts are the asymptotes and the asymptotes are the intercepts. That's a little tricky, okay, of the reciprocals. Okay, what about some more points? How are the curves going? Do I just go like this? What am I doing? Okay, let's check this out. So as soon as I figure out how to back up what I just did there. Okay, where's Mr. Lecky when I need him? All right, so a couple of key points that we had on the tangent curve was that the tangent equaled 1 whenever we were at 45 degrees, okay, or pi over 4. Doesn't the cotangent also equal 1 there? It sure does. So we come up with this dot and this dot. Again, now let's think about negative. When the tangent is negative 45 or negative pi over 4, isn't the cotangent negative 1? Well, it sure is. And so we end up with this dot, because that would be negative 45 and negative 1, okay? So what's going on the curve? We're just going from asymptote to asymptote, going through those 3 dots, and voila, we have a cotangent curve. Again, all 3 of these start from the parent, tangent, cosine, or sine. So whatever we've done to the parent, stretch it, shrink it, flip it, slide it, we do that first, and then we change and do our reciprocals based off of that graph. Alrighty, you might need some colored pencils for this. You're definitely going to need some graph paper for this, and the questions will get a little bit harder, but we'll do those in class together.